In this video, we are going to talk about higher order derivatives. And so the idea here is if f is a differentiable function, then f prime is also a function. So it has a derivative. Okay, so we can, if f prime is also a function, we can take its derivative the same way. We would just take f double prime of x to be the limit as h goes to 0 of f prime of x plus h minus f of prime of x divided by h. And since f prime is a function, this is perfectly fine to do. And as suggested, this f double prime is our notation. And so this derivative is called the second derivative of f and is denoted f double prime of x. So I kind of skipped to the notation. That is the idea of a second derivative. So now using one of our other notations, we'd write this as d over dx of dy over dx, which this is saying take the derivative of dy over dx, so take the derivative of the first derivative, and we write this as dy squared over dx squared. So this is the another notation for the second derivative. So let's do an example of computing the second derivative of a function. So we want to find the second derivative of y equals 3x squared minus 2. So we want to find the second derivative of this function. So let's compute its derivative to start with. And so first we want the first derivative, so dy over dx. This is the limit as h goes to 0 of 3 times x plus h squared minus 2. So this is our f of x plus h minus our f of x, which is just 3x squared minus 2. Then we divide that all by h. And so this is the limit as h goes to 0 of 3 times x squared plus 2xh plus h squared minus 2, then minus 3x squared plus 2, all divided by h. So we have the limit as h goes to 0 of 3x squared plus 6xh minus, or plus 3h squared minus 2 minus 3x squared plus 2, all divided by h. So we have a 3x squared here and a minus 3x squared here, minus 2 here, plus 2 here. And so this simplifies then to be the limit as h goes to 0 of 6xh plus 3h squared divided by h. So we have the limit as h goes to 0 of h that we're going to factor out of the top of 6x plus h divided by h. The h's cancel. And we're left with the limit as h goes to 0 of 6x plus h, which is just going to be 6x. And so this is dy over dx. dy over dx is 6x. But what we wanted was the second derivative. So this is the first derivative. So to get the second derivative, we're going to do this process again. So the second derivative is going to be the limit as h goes to 0 of 6 times x plus h minus 6x, all divided by h. So this is f prime of x plus h minus f prime of x. So we have the limit as h goes to 0 of 6x plus 6h minus 6x divided by h. which is the limit as h goes to 0 of 6h over h, which is 6. And so the second derivative of our function is 6. And so just to kind of summarize what we did, we found first, if f of x was 3x squared minus 2, f prime of x we found was 6x, and f double prime of x was 6. And so we were able to compute the second derivative just by doing the derivative twice. Now, in general, we can think of the second derivative as the rate of change of the rate of change, which is a bit wordy to say, but there is a very common application of it in physics. And so if s equals f of t is the position function, of an object moving in a straight line, then v, which is f prime of t, is the velocity function. We've seen this before. But the new thing is, and a, which is f double prime of t, is the acceleration function. And so if you want to figure out the acceleration of a particle, or of some object moving in a straight line, you take the second derivative of position. So this is the rate at which the velocity is changing. So this is like how much are you getting faster or getting slower inside of a car if you're moving on a straight line or something like this. Now, we will see more uses of the second derivative in the future. But one thing that we want to know is that if f double prime is a function, then it has a derivative. This is the third derivative. So this is called the third derivative of f, and is denoted f triple prime of x. Now, we could keep doing this. There's nothing special about stopping at 3. And so, in general, the nth derivative of f of x is denoted. Now we changed the notation here. It's going to be f, then in parentheses a little n of x. So we put a little n in the superscript instead of using primes. And so we do this when n is greater than or equal to 4, usually. So we get kind of tired of writing the primes. So after 3, we just go to this notation. But this is just saying find the fourth derivative, fifth derivative, or so on. So like if I write f to the 7th of x, this is the 7th derivative of f. And so we could keep doing this as many times as we want. And so we're going to look at an example of computing such a thing. So we want to find the third derivative of y equals 3x squared minus 2. So this is our function from before, just to save a bit of time. So we already know what its second derivative is. So we want to find the third derivative of this function, y equals 3x squared minus 2. So the third derivative, which we write as d3y over dx cubed, it's going to be the limit as h goes to 0 of f double prime of x plus h minus f of x, f double prime of x divided by h, which plugging in our second derivative, which was the number 6. This is 6 minus 6 over h. So we have the limit as h goes to 0 of 0 over h, which is 0. And so the third derivative of this function, 3x squared minus 2, is 0. So f triple prime of x is 0. And now once you get 0 for the derivative, it's going to be 0 from then on. And so in general, the nth derivative of this function is 0 for n greater than or equal to 3, where f of x in this case is the function 3x squared minus 2. So once you get 0, you'll just keep getting 0. That should be fairly obvious when you plug it into the definition. You're just going to have 0 minus 0 on the top. So this is the idea of a higher order derivative. We just are saying take the derivative over and over again.